Hello, welcome again. We are solving GATE 2016 Aerospace Engineering paper. Question number 45 is a wall of thickness 5 mm is heated by a hot gas flowing along the wall. The gas is at a temperature of 3000 Kelvin and convective heat transfer coefficient is 160 watt per meter square per degree Kelvin. The wall thermal conductivity is 40 watt per meter per degree Kelvin. If older side of the wall is held at 500 Kelvin, the temperature of side exposed to hot gas is dash Kelvin. So this is your 3000 Kelvin. The temperature of the gas is 3000 Kelvin, and convective transfer is given as 160, and thermal conductivity wall is your 40. And the temperature on the colder side is 500 degree Kelvin. So there are two resistance in it. One is resistance due to hot gases, and other is resistance of wall. And resistance of hot gases is 1 by HA, and resistance of wall is thermal resistance of wall is delta by K. So as these are in series, so they will be added. Okay, so so H is your 160 and thickness is 5 mm or 5 by 1000 meter. Okay, conductivity is 40. So putting the value and finding out R1 and R2 and then finding out the total resistance. Total resistance is here 0.06375. So as this temperature is known, that is 3000, and this temperature is known, so we can find out heat transfer also. So heat transfer is T minus TCW by R, or it is 3000 minus 500 divided by this R, so it will be 392.156. So heat 392.156. Okay, so not point. So now heat. Now we have to find out temperature on the side exposed to hot gases. So we have to find out this temperature. Okay. So now here there is one resistance, that is convective resistance. So and temperature here is 3000, and here is for THW. So TH minus THW is by R1, and taking this resistance only, we can find out the heat transfer. So TH is 3000 and THW is your we have to find out, and this is your 1 by 160, and this is your total heat transfer, because same heat transfer will take place from this to this and this to this. We have find out that the total heat transfer, so same heat transfer will take place from 3000 to this wall also. So taking the same heat transfer, we can find out THW. So THW is your 549.01 Kelvin. Okay, so answer is 549.01 Kelvin. Next, question number 46. A launch vehicle has a main rocket engine with two identical strap-on motors, all of which fire simultaneously during the operation. The main engine delivers a thrust of 6300 kN with a specific impulse of 428 seconds. Each strap on the motor delivers a thrust of 12,000 kN with a specific impulse of 292 seconds. The acceleration due to gravity is 9.81 meter per second square. Effective or combined specific impulse of the vehicle is dash second. So specific impulse is thrust by weight per second. Okay. And general formula for specific impulse is thrust by weight per second. When we consider the main engine, the thrust is 6300 or 6300 into 1000 newton. Okay, and the weight per second is 4 Wn. Okay, and the specific impulse is given as 428. So we can find out weight per second. So that comes out as 6300 into 1000 by 428. Okay. Similarly, for strap motor, we can find out the weight per second. So so for step motor, the thrust is given as 12,000 12,000 kilonewton or 12,000 into 1000, and the specific impulse is given as 292. So this will be 12,000 and 1000 by 292. So total thrust will be summation of now we have total weight, that is Wm weight per second, total weight per second, that is Wm plus Ws2 plus Ws1, and we have total thrust also, that is 6300 plus 12,000 into 1000, 12,000 into 2 because there are two steps, so 12,000 into 2 plus 6300. Okay, so that is the total thrust and that is the total weight. Now if we divide total thrust by total weight per second, then it will be specific impulse, so that comes out as 312.65 seconds. So answer is 312.65 seconds. Next, a substance experiences an entropy change of delta S greater than 0 in a quasi-steady process. The rise in temperature corresponding to entropy change delta S is highest for the following process. Option A, isenthalpic process. Option B, isobaric process. Option C, isochoric process. Option D, isothermal process. So in isochoric process, the the temperature rise will be more as compared to isobaric process because CV is less for the same heat supply. Okay, for the same entropy change. Okay, and whereas in isothermal process the temperature will remain same. So this is not the option, and this is also not the option. So answer will be either B2, and from this answer should be isochoric process, and because CV is less than CP, so for same entropy change the temperature rise will be more for isochoric process. So answer is option C. Next, in a particular rocket engine, helium propellant is heated to 6000 Kelvin and 95% of its total enthalpy required as kinetic energy of nozzle exhaust. Consider helium to be calorifically perfect gas with specific heat at constant pressure as of 5200 joule per kilogram per degree Kelvin. The exhaust velocity for such a rocket for an optimum expansion is dash meter per second. So total enthalpy at 6000 Kelvin per unit mass is CPT. Okay, so CP is 5200, and the stagnation temperature is 6000. Okay, so that is the total enthalpy, and 95% of it recovered. So it means it covered as kinetic energy. So taking unit mass, so this will be the change in this will cause the change in kinetic energy, or this will be your kinetic energy. So this is Cp T into 0.95. Okay, so V will be your 7. Solving this, putting the values, we have 7699.35 meter per second.